Welcome. I am Katherine Hambleton from NASA's Office of Communications. Thanks for joining us today to talk about some of the exciting science going up on tomorrow's launch. The Cygnus spacecraft is loaded and ready to go atop an Atlas V, which will launch during a 30-minute window beginning at 11:05 today, or tomorrow evening, I'm sorry. Here with me today, actually, just to let you know first, we will be taking questions from those in the room as well as from those on the phone and those online. If you are on the phone, please press *1 to be entered into the queue when you have your question. And for those online, please use the hashtag AskNASA. So we have a lot of science going up on the rocket tomorrow, and here with me to give us an overview of the science going up, we have Pete Hasbrook, Associate Program Scientist from the International Space Station Program, and Dr. Michael Roberts, Deputy Chief Scientist for the Center for Advancement of Science in Space. If you guys could tell us about some of the great science we have.
Be glad to. I'd like to thank you all for joining us this afternoon. We are really excited about tomorrow night's launch and especially about all the scientific hardware that's going up for us to continue our great work on the International Space Station. The Cygnus spacecraft can bring a variety of experimental hardware, a variety of all kinds of hardware. On this launch in the scientific area, we've got almost 860 kilograms of cargo for the science team, which is over 1,700 pounds of cargo, which adds up to about a quarter of the total cargo, I believe, on the Cygnus. Now, the ISS, the International Space Station, is a very versatile and capable laboratory in space, but it's not like most laboratories that you're familiar with on the ground here, which may focus in one discipline of science and maybe one very narrow focus of science. We've got a broad breadth of scientific disciplines. We've got human research, biology and biotechnology. We've got earth and space sciences, physical sciences. We've got technology development as well as education. And to date, across the international partnership, we've had over 1,900 different experiments conducted on the ISS. We've served more than 2,700 scientists across the partnership and around the world. And we've had participation on the ISS program of more than 95 countries around the world. Now, tomorrow's launch will bring supplies to help us continue our work on the space station, to continue some of the experiments that are already going on. But we have several new experiments that the Cygnus is bringing to us. And this afternoon, the speakers that follow us, you'll hear about some of these exciting investigations. We have a planned controlled fire that will be ignited on the Cygnus spacecraft after it's finished its mission with the ISS, after it's unberthed. And that will study the growth of fires in space, and it will help us keep future spacecraft safe from fires. You'll also see an experiment about mechanical adhesion. This is a technology that allows its reusable adhesion. It doesn't leave any adhesive. It's usable on many different surfaces. Most benefit to us is it's reusable on lots of different surfaces. You'll also hear about additive manufacturing, which is the next phase for us in the space program for making hardware out of just raw materials in space. It allows us to build new tools on the space station, replacement parts, and eventually we are looking forward to the additive manufacturing building new experiment hardware for us. You'll hear about an investigation about regolith, which is the impact-shattered soil that makes up the lunar surface, it makes up comets and asteroids. And finally, you'll hear about an instrument to be mounted inside the ISS, which will look at meteors as they enter the upper atmosphere, and most importantly, it'll look at the chemical composition of those meteors, what makes up those meteors that are entering and populating our world here. And so I hope you'll agree with us that the station program, the science program that we have, is advancing the knowledge of our Earth around us, it's advancing human exploration of space, and it is benefiting all of us on the ground. And so I'd now like to turn over to Mike Roberts.
Thank you, Pete. I'm here from CASIS, the Center for the Advancement of Science in Space. CASIS is the manager of the International Space Station National Lab. So Pete introduced to you a lot of the different tools that are available on board the International Space Station, and it can plug in and provide opportunities for research investigations from, as he mentioned, a broad breadth of research interest across the United States. The International Space Station National Lab specializes in providing access to the space environment for a large variety of users. So we are sponsoring on the ISS National Lab investigations, as Pete mentioned, Project Meteor, that is utilizing the International Space Station as an Earth observation platform. So in the same way that we have satellites that orbit the Earth to take images of the Earth, the International Space Station affords unique opportunities from its orbiting the U.S. and the world about every 90 minutes or so. So there are opportunities there to utilize it as an Earth observation platform. There are also opportunities on board the International Space Station for commercial companies to test hypotheses, to develop drugs, and in some cases to actually explore manufacturing capabilities on orbit. So you're going to hear from one of our implementation partners, Made in Space, a little bit later, who's going to talk about what was originally a research experiment, a technology demonstration on board the International Space Station that has now translated into a manufacturing facility, the additive manufacturing facility. That's a very exciting opportunity for a variety of users here in the United States who range from commercial companies who want to explore additive manufacturing capabilities in low Earth orbit, as well as to students. You'll also hear from another implementation partner, NanoRacks, who provides opportunities for research investigations that not only use the International Space Station interior environment, but offer opportunities for satellites to be launched from the International Space Station and go into space. And their customer base includes not only academic investigators and commercial companies, but students as well. So NanoRacks, in addition to its commercial outreach, has a very active STEM program which CASIS participates in to enable access to the space environment for middle and high school students. So we look forward very much to the launch of the rocket tomorrow and to the new possibilities that are going to come from the addition of these facilities to the International Space Station National Lab.
Thank you. We now have some time for questions before we go to our next speaker. For those of you in the room, if you would raise your hand and someone with a microphone will come to you. Please state your name and to whom your question is directed, and please keep it to one question for now, and if we have additional time, we'll go for additional questions. For those on the phone, press *1, and those online, please use the hashtag #AskNASA.
So I'd like to hear more about the additive manufacturing capabilities, exactly what you're doing and what you're trying to accomplish.
And that will actually be one of our speakers that will come up, so we'll be able to talk more about that shortly.
Never mind.
Good question.
My name is Mark Gotch, Historical Space Imagery. Can you tell me, gentlemen, the nanoracks that you mentioned, with its capability of having a satellite, did I hear it correctly, launched from space, from the space station? Will this be, if I am to be looking forward to the future, looking at things like Dream Chaser, being launched, jettisoning into space, will it be then able to dock at the space station, maybe be carrying parts of a satellite and it be launched from the space station? That will be a possibility?
Short answer to that question is yes. So there's obviously a lot of interest with the capabilities of small satellites and nanosatellites to improve the speed of return for taking technologies into the space environment. And rather than having to rely upon a large satellite bus, which is extremely expensive and requires a lot of development time, to actually build your own and do it yourself. And there are companies that are interested in taking that capability from building a satellite here on Earth and taking it into space to launch to actually doing assembly and modification of satellites on orbit. So the International Space Station National Lab is a unique environment because you have the opportunity there to actually assemble different parts, to actually manufacture parts of that satellite on orbit and actually reconfigure before launch or recover and that. So it's the beginning of a whole new market in low Earth orbit.
Just a second part to that question, sir. Again, very aware of the great work CASIS has done in giving many individuals and groups the opportunity to do experiments in space. Was CASIS part of this going forward involving the future of satellites being launched from the space station?
Yeah, so one of the major reasons behind the designation of the U.S. operating segment as an International Space Station National Lab was to provide new opportunities for a whole new range of investigators and engineers to explore low Earth orbit as an environment for innovation, for trying new technologies in the space environment. So those opportunities range from commercial manufacturing capabilities all the way to subcomponent testing, right? So there are a variety of opportunities that are out there, not only for the Earth observation market for satellites, but also for developing new capabilities to develop new areas of research and technology development in low Earth orbit. And CASIS is glad to be part of those.
Thank you. Thank you very much.
Okay, thank you.
Next up, I'd like to welcome Dr. Gary Ruff, Project Manager and Co-Investigator for the Spacecraft Fire Safety Demonstration Project, known as SAFFIRE. Dr. Ruff, I know it's a dangerous thing to have a fire in a spacecraft, so can you tell us why you're going to intentionally start a fire inside a spacecraft?
Sure. The big picture objective, of course, is to learn some things about fire safety in spacecraft that will help us to provide the right equipment and the right procedures and everything for astronauts as they go on long-duration exploration missions. For Sapphire 1 that will be launching tomorrow night, the specific objective is to look at how large a fire can get in space if it were to start on a material, let's say a large piece of material, how large it can get in space, how fast it can grow, and whether it reaches a steady size or it continues to grow in size as it propagates. Now, of course, we've done combustion science experiments on ISS and on the space station before, but in general, they've been about the size of a note card, if even that. On Sapphire 1, what we're going to be doing is burning a sample that's about that big. So if this were to burn on a spacecraft, it would be a big deal. So the apparatus, the Sapphire 1 apparatus, I've got a very small rapid prototype model here. Really, there's two chambers. There's a flow chamber and there's an avionics chamber. And on the end of the flow chamber, we've got 6 fans and 2 fans on the avionics bay, and there's the inlet on the bottom. And if you could bring up the still image, it's shown here on the screen. You can see the sample card, which was this sample sitting there inside the flow duct, and the other part of it is the avionics bay. If you could roll the video. And what you're going to see here is the Sapphire experiment was loaded onto Cygnus in January, and it's going to go up to station. And as they said, one of the important things about our experiment is we're going to stay on Cygnus. So the crew's going to offload all their cargo, all the experiments we're going to hear about, and then load in trash. And then our job really starts once they deberth. It will move, Cygnus will move far enough away from the station, and then we'll have engineers in Dulles at Orbital ATK's facility basically sending commands to start the experiment. And so it'll run through that whole experiment in about 2.5 hours, what it will take to get all of the data that we need, which is going to be primarily video. There's oxygen concentrations, there's CO2 concentrations and various temperatures. What happens when, although the Cygnus vehicle will remain in orbit for about 8 days while they're getting all of our data down. So the experiment is really very short, but then it takes a while to get all of the data that we need back down to Earth. And then what will happen is when we're done, then the Cygnus will just deorbit and destructively deorbit into the Pacific. And so just to conclude, I mean, there's a lot of interaction here between NASA engineers, Orbital ATK, ISS, to make this happen, because this vehicle wasn't intended to do experiments like this, but it's been a great team effort and really fun working with them.
All right, we'll now take questions for Dr. Ruff. Again, please raise your hand, and when the microphone comes to you, state your name. Got a question up here in the front. Just a second.
Hi, I'm Amanda Rourke. I had a couple of questions. Number one, is that the only type of material that you're testing, or is there going to be other types of material that you'll be testing?
Okay, this is the only type on Sapphire 1. Because we don't get these back and you need more data points, we constructed 3 of these. So there's 3 of these units that will go on OA5 and then OA7. On Sapphire 2, we've actually got 9 different samples, and they're different materials. plexiglass. There's a couple of this kind of material so that we can start looking at how variations in size and how that impacts the flame spread. There's Nomex and some other materials that they use on station.
Part two to my question was going to be, is this the last part of the mission before it goes out of orbit? Like, I know they're releasing the CubeSats, so is that going to be before or after the Sapphire test?
It would be before. I don't know when in the timeline, but it's before.
Oh, we have a
Hi, Ken Kramer, Universe Today. I'm curious, are you going to be monitoring the atmosphere besides the material and the fire? Are you going to be monitoring the atmosphere at all?
On this experiment, we have we'll be monitoring the oxygen concentration and the and CO2 at the inlet to our duct. Orbital ATK also has a smoke detector in the vehicle, so we'll be monitoring that. So that's all that we're really getting about the cabin atmosphere in this experiment.
Not any residue from the fire itself, then?
Not in this series of experiments.
What about in the future?
In the future, we're planning right now 3 additional Sapphire flights that will essentially we will use this type of hardware for flammability experiments, but then we'll use the entire Cygnus cabin as part of our test bed, where we will monitor the combustion gases and the cleanup process and the particulate that's produced.
Yeah, very good. Thank you.
Yes, Mark Gotch, Historical Space Imagery. Can you tell me, sir, the ISS as it stands now, has it been developed and made of fire retardant materials? Also, knowing that Earth's atmosphere and how fire reacts to it, have there ever been any previous tests in terms of the contents in space's atmosphere and how it would react to fire involving your test?
Okay, the first question about flammable materials on ISS. Of course, all materials that go up are tested using terrestrial, ground-based flammability tests to find out which ones can propagate a fire and which ones don't. You try to use materials that don't burn and in those conditions, but because people live there, you're going to have some things that they have to use that will burn. And so for anything like that, there's configuration control requirements about and isolation from power sources and all of those things to help make sure that it remains safe. The second question,
I'd looked at and saying, have you looked at Earth's atmosphere in terms of its oxygen content, how fire currently burns? Have there been any previous studies done in terms of space's atmosphere, its contents, and how it would react to fire relating to your experiment, sir?
there have been quite a few combustion experiments in microgravity at 21% oxygen and at other oxygen concentrations. So they've studied it, but again, it goes back towards rather small sizes. And so what we want to do is to start to get to a more, I guess, a dangerous fire if it were to occur in a spacecraft.
I think your experiment should be very valuable, sir. I'm looking forward to hearing the results. Thank you.
Take a question back there.
Yeah, hi, Bill Harwood with CBS News. You haven't explicitly said it, but obviously you don't expect the fire to get out of your containment vehicle, your vessel. So I guess what I'm wondering is why not do it on the space station with the crew to watch it? And if there's a safety threat, what is it?
Ooh.
Thanks.
You're right. We've made it so that the combustion gases can come out, but that the fire is controlled and stays inside our box, because Orbital ATK likes to remain in control of their vehicles, and it needs to come down in the Pacific. The reason that we don't really do this on ISS is the piece that we're not doing on Cygnus that we would definitely have to do on ISS is cleaning up the mess. There is no chamber big enough on ISS to be able to burn something this large. You can burn small things. And a lot of that comes to protect the crew, because if you're going to have it on ISS, the crew has to interact. If they interact, they've got to go into the chamber, which means you've got to be able to clean up the mess. This one, we're not bothering to clean up the mess. In fact, the messier in some ways, the messier the better.
We'll take one more question.
Is ignition source for the experiment like a chemical igniter? Is it electrical? And are there any specific safety considerations having that docked to the ISS for a while before the part of the mission where it deorbits and burns? Like, did you have to think of anything there?
Many things. That's the first question we get. It's an electrical igniter, and just kind of technically, we've got the experiment is powered through 4 relays. They're all individually, can be all individually controlled, and they're all monitored by Orbital. So our avionics is all powered on 2 sets of relays. The igniter is on 2 more, and all of them got to be closed before we can start the software to initiate the experiment. So they're monitoring that throughout the mission.
Will the crew on the ISS have any interaction with that? Like, is there maybe a safety switch that they have to throw as it leaves to like enable it, or is it all software controlled?
It's not all software controlled. There's no switch that they have to do, but of course, Orbital ATK has to, command those relays. The only thing that they have to do is not pack bags around our inlet and our outlet, because you saw that we've got to flow through us. And we've coordinated that working with ISS and the packing arrangements, so we should be good.
All right. We're going to move on to our next speaker. Thank you very much, Dr. Ruff. Up next, I'd like to welcome Dr. Aaron Parnez, Group Leader for the Extreme Environment Robots Group at NASA's Jet Propulsion Laboratory. His work relates to climbing robots and how they might attach to their surrounding environments. And today he's going to tell us about the gecko grippers. Can you tell us how they are going to stick without being sticky in the harsh environment of space?
Yeah, my pleasure. So our work in my lab is all about robotic grippers. We use these grippers as the feet on climbing robots to go up cliff faces, across cave ceilings, or to move around in microgravity. We can also use these grippers as the hands on robotic arms to grab and manipulate things. For this experiment, we're inspired by one of nature's best grippers, which is the gecko foot. And geckos stick using something called van der Waals forces. They have lots of tiny hairs on their feet that allow them to take advantage of these forces. So if we could bring up the first picture. This is a graphic put together by Bob Full and his team at UC Berkeley. You can see on the toe of the gecko are flaps that are on the millimeter scale. You can see these with your eye. But on those flaps grow thousands of tiny hairs called setae. They're about 20 or 30 times smaller than the hair that grows on your head. And at the tips of all of those hairs is further branching, the nanostructure. These are called spatulae. They're much, much, much too small to see with your eye. That's what actually makes contact with the surface, and that's what takes advantage of these van der Waals forces. So if you bring up the next slide, you can see our robotic imitation of gecko skin. We're not quite as advanced as what the gecko has on its foot, and that's limited by current manufacturing capabilities. But you can see roughly the same shape. It has a directionality to it. And that's really important. That's how you turn the stickiness on and off. So if the gecko pulls down on its foot, it's very sticky. But if the gecko doesn't pull down, or if it pushes up or to the side, it's not sticky at all. So this is a good thing. If you're climbing up the wall very quickly and you're using something like duct tape, it might be just fine to get stuck on the wall, but you're going to have to pull with a lot of force to get it to unstick. And this is a big deal in space where there's no gravity, there's nothing to react to those forces. So having the ability to turn your adhesion on and off on command is really powerful. The other thing is it's a very reusable adhesive. So you can imagine if a gecko took 3 or 4 steps and the foot stopped working, that would be a bad evolutionary design. We've tested our robotic gecko skins in the lab 30,000 cycles on and off with no decrease in performance. We've also tested them hanging on the wall for a year and then reused them. And we've tested them in a thermal vacuum chamber at minus 60 degrees centigrade and in full vacuum. Because they rely on van der Waals forces, they're not susceptible to temperature, pressure, radiation, some of the things that make using conventional adhesives like duct tape and super glue not feasible in the space environment. So what we're going to do for this experiment is have the astronauts test 5 handheld grippers. This is the largest of these grippers, and they is a medium size and a small size. And to operate it, you squeeze together, touch down to the surface, and now it's stuck. We've got springs that are loading that material in the proper shear direction. But to turn the stickiness off, you simply squeeze together again. And so you can do this over and over and over again. We're only going to make the astronauts do it about 30 or 40 times. They're going to be measuring what the sticking power is by pulling on different parts of the grippers. And then we're actually going to leave one gripper in place for a full year, just to test the effects of long-duration microgravity. And this experiment is really a precursor to some future capabilities that we'd like to see move up to the International Space Station and other activities in low Earth orbit. For instance, there are many sensors that we'd like to use that require a preload into the surface. Things like accelerometers, eddy current sensors, magnetic flux leakage sensors. But in space, anything you're pushing into the surface is pushing you away from the surface. So using a gecko gripper to react that load could allow us to use those kinds of sensors, reposition them in different places. A little bit bigger in scope, you can imagine using these as the hands on the robotic arms to assemble things in space, to repair satellites, to grab space garbage and deorbit it. Or my favorite application, because my background is robotics, is to put these on the feet of a crawling robot and have the robot go around on the outside of the space station, inspect orbital debris impacts, inspect micrometeorite damage, take pictures, take video, do all the sorts of things you can imagine a robot would be able to do. We're interested in these applications, these space-based applications, but there are a few commercial companies that are looking at making gecko adhesives viable here on Earth, either in a factory floor setting where you might be doing pick-and-place operations with solar panels or cereal boxes, or even in your home. You can imagine this material would let you hang your flat-screen TV on the wall without having to drill into the studs. And when you are ready to move or you just want to switch TVs, you can simply turn the stickiness off and put it on a different wall. So that's the summary. I'm looking forward to your questions. This is our first experiment going up to space station, so we are very, very excited.
All right, thank you. Please raise your hand in the room. Use hashtag AskNASA if you're following online, and *1 if you are on the phone. Again, please state your name, and please try to stick to one question, and if we have more time, we'll come back for more questions.
Yes, sir. Mark Gotch, Historical Space Imagery. Could you tell me, sir, the gecko grip that you currently have that you say the astronauts are going to test in space, right now here in Earth's atmosphere, how much weight will that particular grip support for how long, and how are you expecting that to differ in the environment of space?
Yeah, good question. So a gripper this size can support about 15 pounds on a smooth surface. As the surface roughness goes up, the holding power drops down, and that's because we don't have all of those complex hierarchical layers that the gecko has. We expect it to be the same in space, and 15 pounds of force in zero gravity is actually a lot because things don't weigh anything, right? You're weightless, so you can move around really big objects as long as you keep the inertial forces low. But we haven't tested it. That's why we're going up there to do the work and make sure that that's actually what we see.
Thank you. We'll go back here.
Hi, Ken Kramer, Northeast Astronomy Forum and Universe Today. Talking about robotics, another application I want to ask you about is what about sending these to planetary bodies like the Moon and Mars to go up and down mountains, hillsides, craters, large rocks, things like that? Maybe send one, if these are light enough, on the 2020 rover.
Yeah. Planetary bodies typically are much rougher surfaces. And we actually have different gripping technology that we use for those rougher surfaces. So there's another technology called microspines that are basically lots of sharp hooks. It's also a bit bio-inspired. And that's what we use for our rock climbing robots. And it's actually part of the baseline for the asteroid redirect mission, which is going to grab a SUV-sized boulder using that kind of a gripper. So if you go on YouTube and you search rock climbing robots, or you search crazy engineering gecko gripper, you'll find little YouTube episodes that JPL has put together on these different technologies, and you're free to post those on your sites and all of that.
Here in the middle.
My name is Shannon Stewart. My question is, what's the biological basis for the gecko's hierarchical spine structure, and could that inform the manufacturing technology you need to improve?
Yeah, it's a good question. So geckos have that hierarchy in order to conform to the surfaces it finds in its environment, which aren't smooth composite panels like you're going to find on the space station. And so the hierarchy is really necessary to get all of those tiny, tiny nanostructures in good contact with the surface. And it's absolutely informed our design. There's been a nice collaboration between the experimental biologists at UC Berkeley, that's the slide I showed, and some of the technologists that are trying to make robotic versions of these. We simply haven't caught up to nature yet, but we're hoping to.
And we'll take one question from Ask NASA.
Indeed. Twitter user Derek asks about applications for other missions by saying, is the gecko foot technology to be used on the ARM mission?
Yeah, so the answer is it's not a gecko technology, but it's a similar kind of gripper. So it's also work being done in our lab, but it uses claws. So the geckos use lots of tiny little hairs, but if you think of how a bear climbs a tree, it's using claws. And so we have a technology that's inspired by that kind of claw-based gripping called microspines. That's what's currently baselined for ARM.
Thank you. Thank you very much. And next we have Michael Snyder, who is the Chief Technology Officer for Made in Space. And he's going to tell us about the second generation of a 3D printer heading to space. Mr. Snyder, will you tell us how this one is new and better than the current one?
Sure, I'd love to. First off, I'm the chief engineer. Jason's our CTO. Yeah, no problem. So our AMF is the result of about a 4-year effort that all started with the NASA Small Business Innovative Research Grant, which we were fortunate enough to be awarded. This printer is larger, and a successor to the printer that was launched in 2014 and operated successfully on board through NASA's 3D printing and zero-G experiment technology demonstration. And a lot of lessons we learned from that, including operations, were put into this printer to minimize crew time and to make it a lot more accurate and more functional for the parts we're producing. Part of that, we can produce a lot of parts, or a lot of different materials with this. We're launching 3, which are all plastic-based. First one is ABS, which we've already printed with, and that's like Lego bricks. The second one is a green high-density polyethylene from Braskem, and that's kind of like what you find in food containers at your house. And then the last one is polyethyramide polycarbonate, which is an aerospace-grade polymer, which can actually survive the vacuum, so we can print parts that can survive out in space. First part we'll be printing is an optimized tool in partnership with Lowe's, which is pretty exciting. And we actually also, pretty neat to know, it's not really publicized a whole lot, but we have a scanning technology inside which can do geometric verification of the parts. So there's hardware inside, software from Autodesk. It's called Memento. It's pretty cool. We can actually check the CAD that we send up with the printed part to see how the geometries match. And the whole point of this printer is with Casis, we'll be offering the service for anybody to make experiments, parts. It's part of STEM activities can all be produced with this printer. And that's our hope in the future going forward, just keep iterating, making it better, as the process better and easier for everyone to use.
Thank you. We now have time for a few questions about our 3D printer. Right here in the middle. Raise your hand again, sir.
I'm Das with the Kerbal Space Academy again. Clearly there's a lot of testing that goes into parts that are used in spacecraft. Is there anything intrinsic to the printer's design that helps you test the output of the printer to make sure that it doesn't have internal flaws or things like that? Like, is that something that's being added in?
Yeah, so you can actually, we can bring a picture up of the printer. It's a lot better looking than I am. There it is. And so part of that is the geometric scanning capability I'm talking about, as well as we have real-time viewing of the part that's being produced. Now it goes out in and out with the station signal acquisition, but we're able to optimize that whole process also through software in terms of final inspection. And it's actually made pretty modular, so we can actually swap out systems, including the electrical systems and the filament and the build tray and the extruder, so that way we can upgrade, or not just us, anyone can make upgrades to this and test it out, both here and in space. Yeah.
Got a question up here in the front.
Hi, my name is Rajan Babaria. I'm with Dragon Circuits. I 3D print quite often, as you can see.
I can see that, yeah.
I have this, my iPhone stand. I get a lot of waste. And have you figured out anything about how to recycle some of that stuff and reuse the filament?
Yeah, so recycling's ongoing investigation, both with us and NASA's also doing it. We've made the printer. When there's a failure, it's because we haven't figured out the correct code to send to it. But once this code is figured out, the repeatability is phenomenal, and the maintenance on it, we can tell exactly when we never need maintenance, and it's a really quick procedure. So the common errors that you'd have at home just don't exist, just based upon the part engineering and the printer itself. So it's highly repeatable process, thermally controlled throughout, and so we know exactly what's going on in it. And it's the risk for failure is pretty low for any part that we do up there. But yeah, it's good. Recycling is really important, especially in the future. Yeah.
All right, additional questions? If you are online, please use the hashtag AskNASA. And on the phone, *1. All right. Thank you very much. Next, we have Dr. Kristen John. She's Deputy Project Manager for Strata 1. And Dr. John's work seeks to understand planetary bodies without atmospheres, like asteroids, comets, the moon, and others. So can you tell us why we might want to study this regolith or soil, and how your experiment will work?
Absolutely. Thank you for having me. So first of all, I'll tell you about why we're interested in visiting asteroids before I explain really what regolith is. So NASA is interested in visiting asteroids, sending spacecraft there, and eventually sending astronauts there. But to do this, we have a lot that we need to learn. So asteroids are actually covered with this material called regolith, which is basically impact-shattered material, dust and glass and other particles. So if we're going to send spacecraft and astronauts there, we have to be able to interact with this. So when we visited the moon, we encountered lunar regolith. So this, kind of got everywhere, got in all the systems, got in the joints of mechanical systems. It was pretty dirty. So that's kind of what we know so far about lunar regolith. Asteroid regolith is very different in the sense that an asteroid is a much smaller body, so it has a microgravity environment. So the gravity is much lower. So the regolith on the surface behaves differently. And that's one of the things we're trying to understand, and we don't have a great grasp on that. So that's one thing Strata will address. Another reason that makes asteroids different is the low gravity of these bodies makes it so that if you were to land a spacecraft on there, you can't just land like you would on the moon. You actually have to anchor to the surface. So you have to deploy some sort of mechanism or some sort of anchor to actually hold on so that you don't float away. So that's another thing that we're interested in from an exploration point of view. So I'll talk a little bit about Strata and what we've built. So you can pull up the first picture. Okay, so this is a top view of Strata. So Strata's going into the US lab on Space Station in an express rack locker. So we basically have, what you can see from this top view is 2 of the tubes. We actually have 4 tubes. And if you look here, I've basically got one of these tubes here. So we're sending 4 different regolith simulants up. This is a simulated simulant, so this is just fish tank beads. This isn't actually what we're sending up. But what you can see is in this clear polycarbonate tube, we have the material right here, and then on top of it, we have this device, which we call the entrapulator. Basically, it holds the material in place. So when this is launched onto up to station, during launch vibrations, this stuff won't move around. We're also sending the material pre-sorted by different sizes. So we don't want mixing, we don't want anything to happen until we get up there and activate the experiment. So what will happen is the astronauts have actually very little they have to do for Strata. It's mostly autonomous, but eventually they'll pull it off of Cygnus, hopefully before Sapphire starts. And and they'll put it in place in its express rack location, and they'll basically press a few buttons, and this device here, the entrapulator, will pull up, and it'll give the material room to move around. And that's what we're interested in. So we have a little camera about the size of a credit card looking at each of these tubes. And we'll be taking images over the course of a year. So we're on station for a year because we're basically interested in the microgravity environment that station offers. It's very similar to the microgravity environment you would see on an asteroid. So it works out nicely for us. So you can go to the next picture. Okay, so this is a picture of a couple of our simulants. So we have, as I said, 4 different materials. So this is the first one. Again, it's going in a tube like this, not in a jar like this. This is the simplest model. So this is 3 different beads, all made of silica glass. Each different color represents a different size. So this is the simplest in the sense that for computational models, where we study asteroid regolith, this will be the easiest to analyze afterwards. Each tube gets progressively more complex. So in one of the tubes, we actually have similar material, but we've taken away the spherical shape, and we have basically shards of the silica glass. And then we have another material that's basically a carbonaceous chondrite, which is a type of meteorite simulant that we're sending up. Again, those are size sorted by the different sizes are in different layers. And then last but not least, we have an actual meteorite. So this is the same type of material that make up asteroids. And regolith itself is basically this same type of material that's been shattered over and over again. So it's particles of different sizes, from fine dust to much bigger pieces. So one of our tubes is actually filled with a meteorite that we've crushed up ourselves and put inside. So we'll get on station and we'll basically look at how all these different size particles are moving around. We'll understand what's happening with them, and it'll give us a much better understanding of the dynamics of regolith, something that we haven't studied before to this point. And last but not least, I want to pull up the last picture and just say that we actually have a good team of scientists, all the regolith experts on our team. So there's a lot of people that are very interested in this science. So the effort was led at Johnson Space Center, but we have people from all over that helped build the experiment and help decide what to put in these tubes. So over the next year, we'll be getting back data, and we're really interested to see what we learn about the behavior of regolith in microgravity. Thank you.
All right, we have time for a few questions. Start over here.
Yes, Mark Gotch, Historical Space Imagery. Could you tell me, this strata, this megalite, would you be looking at this experiment in terms of looking at it, maybe bonding it into a building block, if it were, for the future in space, maybe in colonization?
Sure. Yeah. So if you're talking about the regolith in particular, we're interested in the actual interactions, the actual forces, and what's going to happen. So it's something we really haven't studied for more than 30 seconds at a time on like a parabolic flight. So we are interested in the effects of the regolith, interacting with each other. So obviously we have the interactions with the tube that we're taking into account. So this is strata 1. We're hoping to have future versions of this experiment. So we'll learn from strata 1 and build upon that. And decide, what to put in each of the tubes.
Very interesting. Thank you.
And we have one here in the middle.
Hi. So sorry, my name's Amy Kumo. In terms of the asteroid redirect mission, the different asteroids that NASA's looking at, for the composition in the tubes, did you look at those asteroids and make the compositions based on those?
Yeah, absolutely. That's a great question. So some of the folks on our team are involved in the asteroid redirect mission. So one of the tubes is a carbonaceous chondrite simulant. So that's a very, so meteorites and what I call chondrites, or ordinary chondrites, carbonaceous chondrites, are meteorites, but they're representative of asteroids. So this one in particular, this is an ordinary chondrite. It's the most common type of meteorite you would find here on Earth. It's representative of a very common type of asteroid we would find out there. A less common type of meteorite we find is something called a carbonaceous chondrite, and this is representative of the type of body that the ARM mission is currently baseline to go visit.
We'll take one over here.
Ken Kramer, Northeast Astronomy Forum and Universe today. I'm wondering about the volume. How did you decide what volume? I don't see a lot of free space there. This is what I was wondering when you were describing this last week during the audio briefing. If there's not a lot of space, and I'm wondering, doesn't it need more?
Sure, that's a great point. So actually, when this does move back, it only gives it pulls up about an inch and a half or so. So it won't have a lot of space, you're right. And so like I showed, we have a picture of the science team members. And so a couple of those folks are computational people. And so they've, optimized, there's something called the Knudsen number that you take into account the effect of the collisions, the particles interacting with each other with the diameter of the tube. And there's an optimal way to understand how much space you want. So. hopefully that helps.
So it's plenty.
Yeah,
for
it's just
your-
right. It's perfect.
'Cause I would
And
think
if
you
it's
would
not,
need a
we'll
little
learn from this
more,
and,
but
and
no, okay.
fix it for Strata 2. But yeah, we put a lot of thought into exactly how much volume for the space that it'll have to move around. Yep.
Das with the Kerbal Space Academy. How do you anticipate you'll account for the movement of the space station itself, the orbital maneuvers, the boosting? Is that going to affect the experiment, and have you kind of like normalized for that?
Yeah, that's a wonderful question. In fact, we encourage that. Any sort of movements of the space station, any sort of accelerations, the docking of vehicles like Cygnus is actually good for us. That's one of the reasons we're also there for a year. So when you're on the surface of an asteroid, you're going to get impacted all the time by micrometeorite impacts. So we're interested in those type of things. And actually on our experiment, we actually have something called SAMS, which is an acceleration measurement device that's already on station. We actually designed Strata so they can take this SAMS device and mount it right on the front of our payload. And so we'll actually we'll get measurements daily of what kind of accelerations Strata is experiencing. So we actually hope for those kind of accelerations, vibrations. Great question. Thank you.
Do we have any other questions? Okay. Thank you very much.
Great. Thank you.
And next we have Michael Lewis, who is the Chief Technology Officer at NanoRacks. Starting with this mission, NanoRacks will be able to provide opportunities to deploy CubeSats from Cygnus directly after the vehicle departs from the International Space Station. So how does this expand the kind of science that are available to these sort of CubeSats?
Great question. Thank you. Thank you, everybody here. First, I'd like to talk a little bit about our current satellite deployers, and then I'll get to the expanded capability. If we look at this first slide, many of you know that we currently are able to deploy satellites off of the space station. My company, NanoRacks, has deployed nearly 100 satellites this way. Variety of satellites. Shown here, there's 2 Planet Labs Doves. These are Earth observation satellites that take pictures. So if you look at the next slide, this is the orbital vehicle. This is an older Cygnus, but in this mission, in that silver area, it's called the service module. We are bolting a satellite deployer there, and we're going to deploy satellites after Cygnus leaves the space station. So to answer your question, this expands our capability in that we don't have to bring satellites inside and out through the GEM airlock, but also opens the world up to possibly more harmful materials such as propellants. We could have satellites that could propel themselves. Also, this gives us the opportunity to potentially have higher altitude, which is good for our satellites because it increases the lifetime. So, show you another slide here. We have I'm sorry. So, here's the Cygnus you guys are very familiar with. We also have a lot of stuff going on inside of this, and if I may take this opportunity to talk about some of that, we have a total of 29 satellites on this mission. Many of them are going inside, and then later will be deployed out of the GEM airlock system. We also have a total of 8 experiments that are going inside their very small science modules. Actually, next slide, please. So these are our nano labs. We have 5 nano labs on this with a total of 8 experiments. There's one that's a Japanese student project, 2 there from an Indonesian high school, and a number of experiments from Valley Christian High School and Carmel High School in California. These are doing a variety of science, and it's really fascinating that the capability that they're able to do in these small cubes. Everything from an algae water filtration experiment to there's a fermentation experiment using kind of kombucha type stuff. Pretty amazing science, and this is enabled, I guess, through NanoRacks and through our sister company DreamUp. If you guys are looking to put space in your classroom or your classroom in space, I recommend you go to dreamup.org or to NanoRacks and direct you that way. So.
All right, we have time for a few questions now. If you would raise your hand and wait for the microphone to come to you, and then please state your name before asking your question.
Hi, good afternoon. Ray Osborne. I'm just curious with the microsatellites, what are the limitations in regards to, because they're so much smaller than the normal satellites that we would typically see there, what are the limitations with these microsatellites that we send up?
No, great question. So we've actually been blown away by the amount of technology that you can put in this form factor. These CubeSats are about the size of a loaf of bread. Those ones that I showed there were imagers, and they're able to get amazing resolution. You know, they won't disclose how much, but if you go to Planet Labs website, you can see this incredible resolution. With electronics getting so small, you're able to really do some very valuable science in this, and we've seen a variety of that. So yeah, I'd say the limitation more is yeah, the creativity of the developers. So, thank you.
Do we have additional questions? All right.
Thank you.
Thank you very much.
Thank you, yes.
Thank you, everyone, for joining us. We will be broadcasting the pre-launch news conference today at 2:30, and then tune in tomorrow night for live launch coverage at 10 p.m. at NASA TV. You can visit nasa.gov/orbitalatk for more information on this mission, and you can follow along with the researchers on these investigations at nasa.gov/station. Thank you.